All right, good afternoon, everyone. So, I'm going to continue our discussion of PCA today. So last time we learned what PCA was, and essentially it goes like this. We have a data set, maybe points like this, and this data set is in 3 dimensions, and we would like to find some two-dimensional approximation of this data set. So a set of feature vectors that are two-dimensional that somehow best match or best fit the original data set. And the sense in which we are looking for the best fit is the RSS, residual sum of squared errors. So in this case, that means finding this plane, which is the best fit to this cloud of 3D data. The errors between the projections in the plane and the original data points are minimized when the plane is oriented in exactly that way. And if we instead want to find the best one-dimensional fit to this data, we're looking for the best line within this 3-dimensional space. And once again, the idea is to find the line for which the projections of all these points onto that line, or the projection errors for all the points, are minimized when you sum their squares. So that's what PCA is doing. And the way we do this with our data is we first center our data, so we make sure that across our data set, all the components of these feature vectors are zero mean. And then that allows us to compute the covariance matrix like this. And then we compute an eigenvalue decomposition of the covariance matrix, and we sort the eigenvalues from big to small, and then we take the first R eigenvectors, we call those the principal eigenvectors, we stack them in a matrix VR, and that becomes our dictionary matrix. So basically the way that we come up with these z hat i's, these are the coordinates in this new plane. So this new plane is going to go through the origin. So let's see, where is the origin here? Maybe somewhere around here. So this plane goes through the origin. And then if you're wondering like where these different points are in this plane, it's going to be, there's a two-dimensional coordinate system in that plane. And that is exactly these zi's. They tell you where in the plane it is. Or in this case, it's a one-dimensional coordinate system, so the origin is maybe over here, and then zi or z hat I just tells you how far along that line you are relative to that origin. Okay, so these are so now essentially we've taken each one of these original 3-dimensional feature vectors and we've squashed it down to either 2 or 1 dimensions. And this is now how we represent the ith point. And if we want to know what approximation are we doing? In order to reconstruct our approximation of the ith point, you would take that, you would multiply that by this matrix, which would bring it back to the 3-dimensional space. And this is the approximation in the 3-dimensional space. So I guess one important point, just to make sure it's clear. So let's say I'm talking about this right here. So that is the approximation of this data point according to PCA with R equals 1. Right? So there's 2 different ways I can describe this point. I can describe it in this one-dimensional coordinate system where the origin is, I don't know, maybe around here or something. So in that coordinate system, I would describe that red point by a single number. That same red point I can describe in this 3-dimensional coordinate system. And in that, we call this x hat I. So it's x hat I in 3D, or it's z hat I in this 1D. Okay, so both are descriptions of this point. Is that kind of clear? Meanings of these 2 things? They're describing the same point, but they're just using different coordinate systems. Okay. And then we talked about the performance of PCA. We have a metric here which tops out at 1, and so we'd like to make that as close to 1 as possible. But intuitively, as we use fewer and fewer dimensions in our representation, we expect this to decrease. And so we're going to have a trade-off between how many we use and how much compression we do and how good the quality is after we compress. Okay, so now we know about PCA. Now there's different ways to compute it. So as we said here, let me come back. So this is one way to do it, is you build the Q matrix like this, or if you want to write it, this is how you'd implement it in code. You would not implement it with a for loop. You would implement it using matrix algebra. So you would take your data set. So as always, the rows of this each row of that is a data sample. Each column is a feature. So you make your data matrix X. So one approach you could use is you could compute X transpose X. So now you're going to have a D by D matrix Q. Okay. In order to do that, you have this matrix multiply, which could be expensive if you have a lot of data samples. Because every point in this Q matrix is a result of n multiplications and additions. So if n is large, you have n times d squared multiplications to do. So that could be expensive. Also, once you're done with that, you have an eigenvalue decomposition to do. That tends to grow cubically in D. So this could be expensive for large data sets. So, and then the thing about this is once you've done all that work, you're going to actually be throwing out much of the information you computed because you're only going to be computing or keeping capital R different eigen components, and you're throwing the rest away. So you've done all this work to compute maybe all of them, but then you're only keeping some of them. So perhaps there's a simpler or more efficient way to do this. So that's where we get to this thing called the singular value decomposition. So the singular value decomposition is, one of many decompositions in linear algebra. You've probably heard of many of them, like we've talked about the eigenvalue decomposition. Maybe you've heard of like the Cholesky decomposition or the LDL. There's just a long list of decompositions in the linear algebra. Among all of those, I find the SVD to be the most useful, in part because it applies to any matrix. A lot of these other decompositions, like they only apply to a square matrix or a full rank matrix or something. The SVD applies to any matrix, no matter what. And it basically decomposes the matrix into a product of 3 matrices that are intuitive and that can often help you prove things. When you see things in linear algebra, you're like, how do I prove this? Often doing the SVD as a first step simplifies things a lot, and then you can see the structure in it, and then you can see, oh, okay, I understand what's going on now. So so there's basically 2 forms of the SVD. There's the standard one, and it gives you decomposition like this, where U and V are square. And so these U and V are orthogonal matrices. That is the same kind of matrix we saw with the eigendecomposition of a positive semi-definite matrix, or actually a Hermitian matrix. Okay, so this is, I'll write orthogonal here. So U and V are orthogonal matrices. So again, orthogonal means every row is orthogonal to every other row. Every column is orthogonal to every other column. All rows are unit norm. All columns are unit norm. One way we can interpret an orthogonal matrix, if we think about it, is what does it do when we multiply a vector with an orthogonal matrix? So what it does is it rotates the vector. It does not change its length. So when you look at this decomposition, you can think of x as an operator. X is something, let's say when we multiply a vector times x, it changes the vector. This explains that you can think of that change in 3 steps. First, there's a rotation. Second, there's a scaling. So this S matrix is a diagonal matrix, and every element along the diagonal is positive. Moreover, they're actually sorted from big to small. So when you multiply something by a vector by S, all it does is scale each term without combining terms in any way, just scaling each term. And it's scaling each term by a particular number here. Okay, so multiplying a vector by x means rotate, scale, and rotate again. So any matrix multiplication can be thought of rotation, scaling, and another rotation. So it's sort of an interesting observation. And like I said, the key to understanding the structure of a lot of matrices. So this is one way to write the SVD, and it's often the way that's most convenient for proofs, but it turns out that so for a lot of matrices, like anytime you have a matrix that's tall or wide, it's not square, or any matrix that's not full rank, what you find is that there's a lot of zeros in this S matrix. So, and what happens when there's zeros in that S matrix, let me draw it here. You just draw an example of maybe what this looks like. So let's say that X is tall. So you're going to have a square matrix that has the same left dimension as X. Now you're going to have another matrix S, which has exactly the same dimensions as X. And then you have a square one that matches the top dimension of S. Because this needs to match that, this needs to match that. And then let me denote the diagonal entries of S by a little line. So these might be the non-zero diagonal entries, and maybe perhaps you have zeros here. And of course, everything off the diagonal is 0 as well. Okay, so as a result of that, as a result of the fact that there's only a subset of them being non-zero, all of these columns of U don't have any effect because they will be multiplied by zeros. Whatever is there never has any effect. It's basically just zeroed out. And the same is going to be true of these columns of V. They get multiplied out, and whatever is there is basically unused. So as a result, when you compute the standard SVD, and you have a matrix that maybe is very tall or very wide, it ends up computing many, many things that are not, perhaps not useful to you. So there's a shortcut. It's called the economy SVD. The economy SVD basically is doing this, but it's computing only the part of U that matters, and only the part of V that matters, and only the part of S that matters. So maybe I'll draw the same X again. So now it's going to be a U like this, an S like this, and a V transpose like this. And so in this case, all of the S will be invertible. All the elements along the diagonal are positive. Okay, so we call these UR, SR, VR. And it turns out that if this matrix has a rank of little r, then that is the dimension that we're working with here. This is r-dimensional, 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 little r. Okay, so that's the economy SVD. And as a result of the fact that U is no longer a square matrix, you know that all the columns that remain here, they're all unit norm, they're all orthogonal to each other, and so you could write something like this. But you can't really say much about the rows anymore because you've clipped off all those extra terms that would have made them orthogonal, but these are no longer going to be orthogonal. And the same is true here of this, this is VR transpose. So the V matrix, which we're showing here in transpose form, this guy has orthogonal rows, but I can't really say anything about the columns of VR transpose or the rows of VR. So I can say this, but I don't have this other, like this part of the statement is now missing. So maybe we could say orthonormal columns. That's the property that these matrices have. And then S has the same form, except I've thrown away all the zero terms. And so I know that all the terms remain are strictly positive. So as a result, this is invertible, which is nice in some cases to be able to invert that. The very last thing, I don't know if I said it, is that these are actually sorted. So they start big and they grow smaller. So that is also something that is convenient in some cases. Okay, so these are tools that are used very widely, and we're going to see a particular application of them as a efficient way of computing PCA without having to do that big X transpose X multiply that we said takes up a lot of resources when you have a lot of samples. Okay, so that's the economy SVD. How many of you guys have seen the SVD? Okay, all right. It's definitely, wouldn't be surprised if you see it again. It's very useful. Okay, so here's how we can use this SVD to compute PCA. So this is what we saw before. This is one way to do it. You compute Q this way, and then you take an eigenvalue decomposition of this, and it gives you this. And we know certain things about this eigenvalue decomposition. We know that this V is orthogonal, and we know that lambda is diagonal with non-negative terms. And we said we're going to sort them. That's not something that typically happens when you, let's say, ask MATLAB to compute eigenvalue decomposition, but you can always sort it yourself when you're done, and so that's what we've done here. Okay, so that's the old way of doing it. Here's an alternate way of doing it. Let's take this expression, and let's plug in the SVD from the previous page. So X turns into USV transpose. X transpose turns to VS transpose U transpose. And the first thing we see is we have this U transpose U. Because we use the standard SVD, U is an orthogonal matrix, so we see U transpose U is identity. So basically we can ignore it. It just disappears. As a result, we're left with something like this. Let's think about that center thing. So S is going to be, okay, so for most machine learning data sets, is X going to be tall or wide? Tall, right? A lot more samples than features. Let's just draw a little picture. X is tall. Okay, so that an S in the standard SVD, S has exactly the same shape as X. So that means S is tall. S transpose is wide. And they are both diagonal. So in this one, we have some terms here that are non-zero, and then the transpose is the same thing. It's just flipped around. So they're over here. And so when you do that matrix multiply, you get a small matrix with some terms. It's possible, it would be very rare, it's possible to have like some zeros down here, which would mean that there would be some correlation among your data samples, your X vectors. That's very rare. So let's just say that common case is that's not going to happen. So this S matrix would be a diagonal matrix that would have you basically have positive entries everywhere. Okay, and so now, and moreover, these entries we said are sorted. That's the SVD always sorts the entries. So now when you compare this old way to this new way, you see that essentially they're doing the same thing. V in both cases is an orthogonal square matrix. Lambda in both cases is a diagonal matrix with sorted non-negative entries. They have exactly the same form. It's almost like a notational difference. So the terms down here along this diagonal, they would be S1 or Si squared over n, where S are the singular values from this matrix. So because there's a division by n and there's a squaring, these are Si squared over n, whereas originally they were lambda. So now we see there's a direct correspondence between what we can get with the SVD and what we can get with with PCA. But the main difference computationally is that with PCA, you first have to compute Q before you do the eigendecomposition. But for the SVD, you don't. You just give it X directly, your data matrix directly. You never have to compute this X transpose X thing. And from X directly, it will produce for you the U, the S, and the V transpose. We're not using U, so forget about that. You just use the S and the V. And that is the information we need for PCA. Okay, so it's just in some sense a shortcut where you don't have to do this step. Okay, so the quantities V and the singular values S from the SVD are sufficient to compute PCA. So in particular, we have this relationship. If we ever saw an expression before with lambda j, now we know we're just going to be using Sj squared divided by n. Okay. V matrices are the same. Okay. All right, any questions so far? Okay, now, but what did we say about the standard SVD that suggests that it's not as efficient as it could be? It's doing what? Think of what we're going to do with PCA as the next step, now that we know our V matrix. What are we going to do with it? What are we going to do with the V matrix as the next step in PCA? We've computed the V matrix. What's the next step? Let's see, sorry. Summary, okay. So once we computed Q, when we took our eigenvalue decomposition, which gave us V, what is this VR? It contains only a few of the eigenvectors, not all of them, right? So with the SVD or PCA, you first get all of them, and then you throw away most of them and keep only capital R. So that seems a bit wasteful. This economy SVD does not compute all of them. It only computes the ones you need that actually define X. And we call that number little r. Little r is the rank of the matrix. Big R is the approximation rank. Is big R smaller than little r or bigger? Smaller, right. So the economy SVD is definitely computing even more than we need. It's computing less than this, which is great, but it's computing more than we need. But it's sufficient for us to use the economy SVD instead of the standard SVD. So that's what we're going to do. We're going to compute PCA with the economy SVD. Okay, so it computes only the top R singular vectors. R, which is the rank of X, is at most either the sample size, n, or the number of original features in our data set. It's the smaller of those two numbers. Typically, D is the smaller one. Right. So this economy SVD is computing, like matrices with D columns instead of n. So maybe way fewer columns. So that's a lot less work. Okay, so that's what we're going to do. So, more efficient to use the economy SVD computing PCA because typically we are going to keep many fewer than D, many fewer than the rank. So this gives us a reduction, and we're still going to be a bit wasteful. We're still going to throw away some of what the economy SVD gives us. Okay, so what we do is we take the economy SVD. It returns these three things. The U matrix, which actually we're going to throw away. We're not using that. This XS matrix, which is diagonal. That contains our singular values. And this V matrix, which contains all the columns that define X, and we're going to throw away, or we're only going to keep the first R. Okay, and that's going to give us our V capital R matrix. Once we know that, we can compute our approximation of X. Call it ZI here. I think I called it ZI hat before, but we'll just shorten it to ZI here. Okay, so this is sort of a summary of how we're actually going to implement PCA. Okay, data matrix, economy SVD. Focus on this, keep only the first R columns of it. That is our dictionary matrix, and that is how we can compute our, you can call them code vectors, latent vectors. These are the things that contain the image about Xi. This U, we're going to basically throw that away. Now, so far we haven't seen a use for the singular values themselves, but there actually is a use, which I'll show you in the next slide. But are there any questions about the procedure that we're going to use now? Okay, so this is how, we'll see this in Python, basically this procedure in a few slides. Okay, so let's say we've computed the PCA coefficients, which basically have compressed our features. Now, that's an unsupervised task in the sense that we didn't use any targets or labels to do that. We just used a collection of feature vectors. But it could be that we actually might have some targets, and we might want to do something like classification with our new feature vectors. So these new features are ZI, where we used to think about the data as being XI, YI. Now our data is ZI, YI. And so when we did this previously, we saw that a lot of methods wanted us to first standardize our features, meaning remove the mean and scale the variance on every feature, the sample variance, so that it was 1. So let's say that this is a good thing to do in general, and let's say we want to do this again. Okay, so we're going to use them for classification. These are our new features. Okay, so standardization, when we talk about our new features, means that our sample mean of Z should be the 0 vector. In other words, these are the ZIs we have across our whole data set. If we average all the ZIs across our n data samples, we want to get 0. So that's taking the mean out. Now, assuming that the mean has been taken out, we also want that the variance equals to 1 for every one of those features. So this is for the jth feature. If I look at the average over I of the squared jth feature, we want that to be 1 for all our new feature indices. So this is like our new number of features. We started with D features, but we squeezed it down to R, capital R. Okay. So we want that this is unit variance. All our new features are unit variance. Okay, is everybody with me so far? So there's a slightly easier way to think about this. It seems more complicated at first, but it's easier to work with. So if you compute the sample covariance matrix of our new features, that would be like the average of Zi transpose. So Zi is a column, Zi transpose is a column, their product is a whole matrix, and then you average that matrix over your n data samples. You get your sample covariance matrix for your new features. If you look along the diagonal of the sample covariance matrix, that's where you get these variances. So when j is 1, that's the first element of the diagonal. When j is 2, that's the second element of the diagonal. So essentially, you want that the diagonal elements of this sample covariance matrix all equal 1. So the diagonal of this equals the 1 vector. Okay, so this is just a simpler way of stating this. And it's simpler in the sense that this is easier to analyze, as we'll see in a second. Okay, so this is our goal. We want these things. We want those two things. Okay, let's see what they actually are. Actual values. So let's start with z hat. Okay, how do we compute z hat? Well, z hat is the average of the zi's. So this is zi. How do we compute zi? Well, zi is VR transpose xi. Okay, so that's what z hat actually is. So now we can simplify this a little bit. Let's take this matrix multiplication and slide it out of the sum. So now the sum is applying to xi. But what is the sample average of the xi's? 0, because we said from the very beginning that we already subtracted the mean. So the sample average, sample mean, is 0. So if this vector is 0, then this matrix times 0 is also 0. So turns out we don't have to do anything in order to make sure our new features are 0 mean. They're 0 mean automatically. So that's convenient. So great. So that's done. What about this property? So let's take a look at our sample covariance matrix. By definition, it's this. Let's do the same thing where for zi, we plug in that expression. So we're going to get VR transpose xi times xi transpose VR. And I did a similar thing where I slid this sum into the center so that it's only applying to my xi's. And the reason I did that is so that this term can be recognized as the original sample covariance matrix we called Q. Now Q, we can write that in terms of its economy SVD. So the economy SVD of Q is VR times SR squared times VR transpose. Okay, so, and then we have, this is a V little r and this is a V big R. So let's maybe just remember what this is. So V little r, and V big R looks like this. So whatever columns are here, I just took the first R of them. I just copied these, put them here. And I threw away all these other ones. So that's what happened when we go from V little r to V big R. But importantly, each of these columns is orthogonal to all the others and its unit norm. So that means if you do, this is like sort of a set of inner products. This is a matrix that contains all the inner products between these guys and these guys. So it turns out that this matrix here has this form. There's an identity matrix, and then there's a big zeros matrix. So the identity matrix comes from the inner products between these guys and these guys. They're the same vectors, they're orthonormal, and they're orthonormal. So as a result, you get IR. This is basically your big R transpose V big R. And now this other stuff here comes from inner products between these and these. Since these are orthogonal to these, and these are identical to these, then these must be orthogonal to these, which means that their inner products are all 0. All combinations of inner products are 0, and that's where you get this zeros matrix. So as a result, what this does is it just is like an I0 matrix. And when you multiply that times this, it basically keeps the top half of this matrix and throws away the bottom half, because the zeros here kill the bottom half. When you do it over here, the zeros kill the right half. And then what you have left when you're all done is just the upper left corner of that matrix, which just contains, it's a diagonal matrix containing your capital R singular values, and then this division by n we're putting here. Okay, so again, this stuff simplifies down and acts essentially just to extract the capital R singular values and throw away the rest. So that is what this QZ matrix is. We would like this matrix to be the ones vector. It is not, but it's very easy to see how to change that. You can see that you wish this was 1, but you can see exactly how it's scaled differently than 1. And so if we just incorporate like the inverse square root scaling, we can, if we scale the zi's by the inverse square root of this, you will get some new scaled zi's that have this property. The reason why we do the square root is because there's 2 of them. So those, we square root of this times square root of this combine to give the right scaling. Okay, so finally, this is what we need to do to get standardized features. Standardized version of z is given by this z tilde, where all you have to do is look at the jth feature and multiply it by root n over sj. And that normalizes it, and now you have a new set of features that are standardized. You only need to do this if there's some reason to standardize them later, like if you're doing classification or you want them to be standardized in this way. Okay, so that's, all right, any questions? Okay, so I think that's it for the math. So now we just have some code and examples. So this is how we do it. So someone gives us feature matrix. We first have to figure out what is the mean. And by the way, the feature matrix in this case, if you remember, these are the faces. So we have faces that have, there's 1,850 pixels in each face, and there's a total of 1,288 faces in our data set. Okay. So let me draw this. So this is an example which is a little bit maybe non-standard in that we actually have more pixels than examples. Okay. So first thing we do is we compute the mean. Now when you compute the mean of a matrix in Python or MATLAB, you have to tell it which axis do you want to average over. So here you say axis 0, and what it will do is it will look at the mean of every column. And so that will give you a vector of means, one for every 1,850 feature. You want to subtract that from x, but of course, this is a matrix, this is a vector, so you use Python broadcasting to turn that back into a matrix, and that will subtract this quantity from every column of x. So, okay, so that's how we get our mean subtracted excess. So now we give that to our linear algebra SVD command, and here we tell it full matrices equals false, which means economy, and it returns for us a U, S, and V transpose. MATLAB is a little different. It's USV, NumPy, USV transpose. When we look at the shape of V transpose, it should match, it should match the shape of this. So here we see it is 1288 by 1850. So it's giving us the shape we expect. And next thing we can do is we can compute the proportion of variance, which is going to be an indication of the quality as a function of how much compression we do. So for that, we need to compute lambda. And we saw that lambda j is sj squared over n, where sj is the singular value. So we can square that singular value, or let's see, I believe that in here this is going to be a vector. So we square the elements in the vector, we divide by the number of samples in our data set, and we get our lambda vector. And now we're going to plot as a function of the number of principal components, which is r, the proportion of variance. And so there's a fast way to do this with this cumulative sum command. And so as a function of r, you can see the proportion of variance quickly increases, and already at about 400, it's already very close to 1. Which tells us that if you're doing something like, if you're working with these features, you should probably be able to compress them almost perfectly using 400 features rather than 1288. Oh, actually, let's see, yeah. Or certainly 1850. So there's a lot of redundancy in these images, basically, in these faces. There's a lot of kind of wasted redundancy in how the raw features are composed. But it would also be interesting to consider, even fewer features, like more compression, where you don't have POV close to 1, it's less than 1. So we'll look at those pictures too. So, the correct interpretation would be 400 principal components captures nearly all the variance of your data. So you have this point cloud in 1850 dimensional space, but you can come up with a subspace of size 400 that almost perfectly captures all the samples. There's very little energy outside that subspace. Okay, so here's the cool pictures. So we're going to look at two faces here. These are the full faces from the data set. And here is the PCA approximation as a function of the number of elements in our dictionary. So this is the absolute simplest you could do, approximating that face by 1. So let's be clear what we're doing here. So on the bottom, I'm showing the mean across the data set. So this is like the average face of all faces. And then this is the most important, the most important eigenvector plotted as a matrix. So this has this kind of subspace, or this direction as you deviate from the mean, has the most energy. Basically, the mean plus and minus scalings of this. They call these things eigenfaces. So that's your first eigenface. This is your second eigenface. So if you're doing, and this is your third eigenface. So for example, if we're doing an approximation of rank 1, that means we're taking the mean, that's kind of like where we start, and then for every image, we're finding the single scalar that multiplies this deviation from the mean. And so like for this image, we found one scalar, that's going to be our ZI scalar, that gives this. For this image, there's a different zi, zi prime that gives this. They look almost the same. Maybe if we would have chosen two faces that weren't both George Bush, we would have had more variation. But as you can see, these are pretty bad approximations to the full face. Not surprising because we've compressed all the information down to one number. Okay, so what if we consider three numbers? So now we're basically, our dictionary is this. It's our mean plus variations that we can create with those things. You start to see some differences. The main thing you see here is a lighting change. Here, the light is coming from here. This is in a shadow. Whereas here, the light is coming from here. This is in shadow, right? And that's essentially, you can kind of see that from here too. This is like lights coming from down here. This is like lights coming from here. This is maybe a light coming from mostly head on. So it's a lot of deviations in faces is really about illumination changes.
So would it be the mean of the first two, like J0 and J1, or mean J0, 1, and 2?
This is the number of principal components. Yeah, so this is like R equals 1 would be mean plus some scaling of this.
Okay.
Yeah, the mean is always like, we took it out at the very beginning. We do all the stuff we did in this chapter, and then at the very end, you add it back in to actually get, yeah. Okay. Okay, and then if we do 10, you're starting to already get, better approximation of these. Still pretty bad, but hey, it's 10 out of 1,850 features. That's a massive compression, right? It's like a factor of 185. Okay, so what if we go up to 30? Well, 30, you start to get, an approximation of the original faces. And once you get to 100, which is a compression of almost 20, it's pretty significant, it's pretty good. Like I would say these are just, they capture the information, they're just a bit blurry. And then once you get to 300, which we said 300 here, 300 is almost perfect. It's pretty hard to tell the difference. I mean, yeah, you can kind of see a little difference, but it's hard to see much difference in those, right? Compression is almost lossless at that point. Okay, so it's I think it's a nice little experiment. Nice way of understanding eigendecompositions. All right, any questions on this? Okay, so let's see what we can do with classification next. So, because we do have labels in this training set, we have, I'm trying to remember, I think we have four people. There's like George Bush, Colin Powell, Gerhard Schroeder. I can't remember who the last one was, but we can try to predict from the face whose face it is. So we just have to do the standard stuff. Let's see. So what we're doing here, I guess this is maybe redoing some of what we did before, because here we're doing the SVD again. Basically, this Z is going to be the matrix of compressed features. So this is just kind of a fast way of doing that. And this is the standardization that we said we need to get. If we want our new features to be standardized, we need to divide by the singular value and then multiply by the square root of the number of samples. Okay, so now we have a set of features that are compressed, but they're standardized. So now we can just do SVM. Here we're doing SVM basically in 3 lines. So we we set our parameter grid out. Remember with an SVM, it's really important to jointly tune C, which is the regularization constant, and gamma, which is the kernel width. Those two things affect each other. They have to be chosen together. You can do that with grid search CV. Cross-validation equals 5. You give it the parameter grid above. And then you just do clf.fit. And it tells you what is the cross-validation accuracy for this classifier. And we're getting 85%, which is pretty good. So let's see. So this was... Okay, yeah. This was done on the compressed faces. So I didn't do it on the original faces, but it would be an interesting experiment to see how much we lost. Now that we've trained the classifier, if we're given a new test image, we have to do exactly the same steps to it to use this classifier for prediction. So you take your test sample, you have to subtract the same exact mean that you used for the training. You don't want to compute the mean of some test set and subtract that, right? We've talked about that before. Way back in unit 3 or 4, we said when you do standardization, you compute the mean and the scaling, the variance on the training, and those are the values you apply to the test. So that's what we're doing here. We're shifting it. We are compressing. We are scaling. And then we can do dot predict. We get a y-hat. And this is on the test set, we're getting 83% accuracy, which is not exactly the same as cross-validation, but we expect them to be pretty similar. Right? So when you do your projects, you have all these possibilities available to you. You're just given one training set. So you need to split that up yourself somehow to cross-validate. So one way to do it is to do k-fold cross-validation, where you have no explicit test set. You just have this set, and you kind of shift around these partitions, and you compute cross-validation here. Another thing you could do if you want, which is typically what we do for neural networks, is you just make one partition into training and test. You train on one, you test on the other. It's just too expensive with neural networks, in most cases, to do k-fold cross-validation. So this is another approach, and you can see that both approaches give you reasonably similar results, but not exactly the same. I would say that this one is probably a little more trustworthy because this has many different splits of the data, and this has just one split of the data. Now, when you go to Kaggle, and you may have gotten some k-fold accuracy, or you may have gotten some holdout test accuracy. When you go to Kaggle, you're going to have a Kaggle accuracy, and that is going to be measured on. Let's see, how is this done? So there's. So Kaggle knows about two things that you don't know about. It knows about a certain set of test samples. It knows how to score your model on the public test samples, but it also knows about a private set of test samples that you will never have any feedback about. So that you'll only see your score on the private test samples once the competition is over, once your projects are submitted. Okay, so usually, and these are just random splits of some big data sets, so usually they're very similar, but a little bit different. So maybe the person that's winning the Kaggle competition going in may not be the person that wins later, because maybe they have overfit to the public testing fold. They have done so much experimentation and submitted so many results to Kaggle, they have started to overfit to that Kaggle score. And so when their model is tested on data that they've never gotten any feedback about, it might be a little worse. So that's how these things sort of manifest in the project. So in the project, you have all sorts of different ways to measure quality. You have your training, RSS, or R squared. You have your cross-validation, like this. You have test, if you split into training and test. You have Kaggle, 4 different metrics, right? So when you write your reports, make sure that it's clear which one you're talking about. If you just said like, our R squared got better, which R squared? Maybe your training one, got worse, but then your CV got better. Maybe the opposite. It's important to make that distinction. Okay. All right, so we're almost done here. Only a couple more slides. So I tried to say this earlier, but we have to be careful about PCA because it throws away a lot of information, and sometimes the information it throws away could be super important to us. Basically, PCA is 2 things. It's linear, and it minimizes RSS. Okay, that's great. They allow us to derive a closed form solution, but it's maybe not what we should be doing. So let me show you an example of PCA in classification. So imagine that this is our data set. It's a 2-dimensional data set, 2 features. And it's labeled in this way. So we have class 1 here, class 2 here. So as you all know, if I had the full data, no compression, no PCA, and I wanted to design a classifier boundary, I would put it somewhere like here, right? Now, which dimension or which subspace of the data is the one that's important for distinguishing the classes? That if I go to the northeast or if I go to the northwest? Which one is important for classification? Northeast, right? This direction takes me over the boundary or not. This direction doesn't help me at all with classification. The information this way is kind of orthogonal. It's completely apart from what I need to know to classify well. So the problem is what PCA will do is it will look for which direction do you have the most variation in your data set. So this data set, it's mainly stretched this way. So most of its variation is this way. So it says if you want to compress this down to a line, the best place to put that line would be right here. So it would project all these samples onto that line. And then you'd have a bunch of samples on that line. And do you see what you've done? You've thrown away all the information that you need to do classification. You've reduced to all the stuff that doesn't matter for classification. So PCA threw out it did what it was asked, but it just threw out what was important. So this is an example of where PCA can go wrong, and it's not designed to necessarily work well with classification. It might work fine. We saw like with the faces, it worked fine, but it might also not work fine. So it really depends. So if you're wondering, well, like what's the right thing to do? If we really want to reduce dimensionality so that it works well with classification, there is a classical technique called linear discriminant analysis, which is just a different way to do dimensionality reduction that knows about the labels, and knowing about the labels, it figures out the right way to compress the data. So I'm not going to say anything more about this, except to point out that it exists. It's kind of a classical method. I don't really see it being talked about today, but it's certainly like what they would have taught, in classification or in machine learning courses like 20 years ago. So and longer. So there are things you can do that are better than PCA in this case. Okay. So the very last thing I want to talk about is data visualization. So one of the main uses of PCA is just to reduce a complicated high-dimensional data set down to 2 dimensions so that you can visualize it. So here's one case where we have 3 dimensions. It's kind of hard to see. You could maybe rotate this around and get different views of it. But if I do PCA, it would say project everything in this plane, and then I can just look in the plane, and I can immediately see that there's a nice structure to the data. Okay, so that's something you could do. The main point is that we've reduced it to 2 dimensions so we can visualize it. So that's not a very interesting example. What if we did this with MNIST? So if you remember MNIST, I think it's, I'm to remember how many features. There's like 384 or something. It's several hundred features are in MNIST. And what if we squashed MNIST down to 2 dimensions? And then for each point, we colored it according to the class. So you get this picture. So like all the zeros are here, all the ones are here, all the twos are here, and so on. And so this alone, as you can see, well, it's not really doing a great job of separating the classes, right? It shows us some interesting structures. And actually, so this is the first principal component. This is like the eigendigit, if you will. And let's say blue is positive, red is negative, gray is 0. So this is like a shape that has like a ring, and then it has like a negative trough in the middle. And this is the most important subspace of deviation within the MNIST data. And it kind of makes sense. When you look at these are the zeros, these are the ones. They are like the opposite extremes, right? If I go this way, I'm going to enforce the blue. If I go this way, I'm enforcing this, and you get those extremes. Now, of course, there's more variations in MNIST than just those 2 shapes. So the second principal component looks like this. And again, this is going to give you a really crude approximation of the true data, but you can imagine that using these 2 things, you can start to build some more interesting shapes. Like this has these vertical lines that will help you with like 8s and 3s and 9s and so on. And it also has like a curve here and so on. So for example, if you go straight up and you're kind of close maybe to the 9 territory, that's because maybe you're using this shape to make a 9. Or if you go down, you're in the 2 territory and maybe maybe a 2 has like, you're using those things but not so much those, and so on. So you can kind of understand how these principal components relate to how the data is structured here. Okay, so it's sort of an interesting visualization, but not super useful because a lot of these classes are overlapping. So again, PCA is just a super simple tool, very classical tool. People don't use PCA for this. They use nonlinear techniques that have been designed precisely to do this. So the currently most popular ones to do this are TSNE and UMAP. And let me show you examples of MNIST with TSNE and UMAP. And you can see they do a great job of coming up with some sort of way of visualizing that data set in 2 dimensions where you actually do have separation between the different image classes. Okay, so there's a little bit of tweaking when you use these. There's a few parameters to adjust. You get different pictures. But they, if someone just gives you a data set and you know nothing about it, you don't even know whether this data set can be classified. You're worried that maybe it's just too hard to classify. There's too much overlap between the features for the different classes. As a first step, you could just give it to TSNE or UMAP, play around with it, and if you can get a picture that looks something like this or this, then you know there must be a classifier out there that I can design. It's worth working on. But if these tools cannot separate the data and everything that looks overlapping, then you might be like, this might just be too hard of a data set to do anything with. So it can be useful as just a visualization tool for techniques, for a brand new data set. Especially if you're, like one of the things you might do is you might try, someone gives you a raw data set and you're like, okay, I want to come up with some feature transformations. I want to do some pre-processing to maybe get useful features out of it. You can do different types of pre-processing and then visualize things this way and get a sense for which pre-processing is going to be the most useful. That's one way to do this. Okay, so that's all I have to say for this unit. Sorry I went over time. Any questions on PCA or dimensionality reduction? Okay. A lot of these things will come back to us in the next and last unit on clustering. We'll see an alternate approach that is similar to PCA but very different called non-negative matrix factorization. And yeah, we'll learn about some new stuff too. All right, see you guys on Friday.